Hello everyone, welcome back to optimization techniques subject. In this session, I'm going to continue our discussion about RSF method. In previous sessions, we have started to discuss about the optimization process in RSF method. And I have introduced you an example which we can consider the optimized point in the uh, process or the process space actually as a, peak of a hill. And I said when we are from the peak of the that mountain or hill, we can see that the peak, and a linear model will help us to go closer to that peak or to the optimum region in the design space like what we have here. So linear, as you can see here, a linear model, first order model, will help us to get close to this optimum region. But this method which we used was the steepest ascent method, which we used to get closer to this optimum point. But this method is not only useful to help us to get closer to the optimum region, it will also help us to understand when the first order model is not is no longer valid, and we need to go for a more complex model which can help us to reach the optimum point in the process space or experiment space. And also we can get this information and we can check if the model is not valid by lack of fit, by checking the lack of fit of the model, which I hope you all already know about that. I will go through this concept lack of fit for the model in a specific station, and we will calculate lack of fit for a model. However, you suppose you already know about this. So lack of fit also will help us to understand if the model is valid or not. It shows the model is showing accurately the correlation between factors and response or not. And also, so when that first order model is not valid, we need to go for more complex model like second order model. But before we get this model or find this model, we need to have additional levels and extra data points or more levels for the factors. For example, temperature. In for linear model, we only can find the model by two levels: 20 degrees Celsius, 30 degrees Celsius, low and high, for example. But and it the linear model is something like this. But when we go for the second order model, it can be also like this. So we need more level in our design space factor response, like what we have here. So we need to increase, here you can see also the extra level which we need. And also extra data point means more run or more experiments, actual experiment is required to get that second order model. But how many levels? Usually it is five levels, is five different levels is for each factor is enough to get a robust second order model for our experiment space actually. So that second order model can be something like this. You can see here the constant in the model, the main effect, and also interaction effects of the model, second order effect of the model, of the factors. And generally, the model which can help us to get the peak in the process space is equation like this. To find this equation, we need to at least have three levels and enough data points in our matrix, experiment matrix actually. So after we have that three levels for each factor, for example, here for three factor, you will have a mathematical model like this. However, maybe not all of the terms will be significant, but the general form of the model, which can help us, for, uh, for example, here for three factors, is something like the second order model for three factors with three different levels. We can use two different designs to get that second order model. This model which we have here to find the optimum point actually in the process. So these two design are central composite design and box Bacon design or CCD and BBD design. Most of people just know RSM because by these names, CCD and BBD. These two designs actually will help us to optimize the process as well. And the similarity between these two designs is both of them are an development of the factorial design actually. We will see more detail about them. First, let's see how is the uh, illustration of these two designs. If you remember, this cube is design space for the three factor for a factorial design of experiment. We add this center point and also some axial or star points to our design space. For example, if this is low, this is high for this factor. You know, here is something like this: x1, x2, x3. I think you are familiar with this box for factorial design. And in factorial design of experiment, we have, for example, if x1 is temperature, we have low temperature, high temperature. Now we add also the extreme low temperature and center or medium temperature and also extreme high temperature to that factors. And we have also we do same for all of other experiment. And this is the design for this is CCD design actually, central composite design to find that second order model. We add more level to the factors, then we can find that second order model with these new data points and new level for the factor. And the box Bacon design is like this. You can see here. You know, if we compare this with the factorial design, we have changed the position of the factorial point from the corner of the design space box to the mid point of edge of the design space. If you compare this, it is shift to here. In this figure, you can see that. And later we will see more about both of these two designs. Let me start with CCD design, CCD or central composite design. In this design, each factor varies over 5 levels. These levels, as I told you, and we will see later, is extreme high level, center, which is a medium amount of that factor. For example, if it is temperature, this can be 100, this can be 50, this can be 0, negative 50, and negative 100, for example. Levels for uh, factors which we can have in the central composite design. So in this design, at least we have 5 levels for each factor. And this design is usually bigger than box Bacon designs. We will see later for box Bacon design, we have 3 levels for each factor. Here we have at least 5 levels. And if you notice here, this design is uh, created based on the factorial design. We had this for factorial design main uh, or factorial point, center point. For example, low, medium, and high for this factor, it is, for example, x1 and x2 in this direction. Also, it can be low and high, for example. Then we combine that and we add that star point to this factorial design, and we will have these star point which are out from the for this in this case we add these star point which are out of the design space which we have for the factorial design. And as you can see here, so we will have factorial point, center points, and axial points in this design. And one more thing about the CCD is we call this design as a rotatable design. Later we will see what I mean from this rotatable design. What I told you about the combination of factorial point with star points for three factors. This one is for two factors. Here we have for three factors. You can see here design a space for factorial design for three factors. We combine that and we add star points or axial points to that design. And then we will have a central composite design or CCD design. And you can see here three factors, factor 1, factor 2, factor 3, and Q point or factorial point. Axial point and center point which we have for this design. This axial point which we add to the our matrix of experiments is like this. They are located in distance from the center of the design space or design cube or design rectangle what we have here. This distance is called alpha, and we need to calculate this alpha according to the number of the factors. For example, for an experiment which we have three factors like temperature, pressure, and time, for example, it means k is 3. We will have 6 axial points like what we have here. We will have 6 axial points, uh, and the the amount of the value for each factors for these points for this each one of them is one actually. Here is x1, x2, x3. The amount of the value of each factor in each one of these axial points can be written like this. The positive alpha 0 0, which we have, this alpha is distance from this center point as you can see here, so we call this alpha. You can see here in two factor it is more clear to understand the factor. The value for this factor is located at this distance from the center point of the design space. And this alpha is usually chosen so that the CCD or central composite design can be rotatable. Later, as I said, I will discuss about what is rotatable. But if we want to have a rotatable CCD design, we need to select alpha according to a table which I will show to you. And in this design also, we need to have at least one center point and the center of the design space, like this star which we have here, which is values for x1, x2, x3 will be 0, 0, 0. It is the origin actually of the coordinate system for the factors actually. And usually we need more center points. Later we will discuss about that. What is roll of center points, and usually we need more center points in the software, especially we see that to calculate pure error of the model. We will see later also about pure error. Just to what you need to know in this slide or in this lecture is you need to select alpha according to your objective of the design. If you are going to have a rotatable design, you need to select alpha according to this table, which is related to the number of the factors. If you have two factors, temperature and time, alpha will be 1.414, and if the factor is 3, alpha will be this much, and so on. So we if we do this, the our design will be rotatable. But if we select alpha equal to 1, then if you notice here, for example, or here, the distance from the center will be 1. However, it is not rotatable. In rotatable design, actually, this we have something like we have a circle can cross all of these star points, and the factorial point will be located at the center of this circle. We call that a rotatable design. And for a rotatable design, the variance of the predicted response is constant at all points that are equidistant from the center of design. So if our design is rotatable, it means it doesn't dependent on the uh, it doesn't depend, the model will not change due to the changes in the runs which we'll have in the for the experiment. So the rotatability is an advantage of the design. Is it can be for all type of design of experiment, even factorial one. But this is also an advantage of CCD design, that our model is not dependent on the direction which we choose to develop the model. In software, we will see about that. We need to select alpha according to this table to have a rotatable design for CCD. In a rotatable CCD, all points lie an equal distance from the center, like this. And a star point actually lies on a sphere which circumscribes the factorial design, like this. These grain balls are located in those circles, which will circumscribe actually the factorial point. This type of CCD provide equal error prediction unit from the center, independent of the direction. It is an important property or parameter which in software usually will be helpful for us, and we need to notice about that. Uh, and this is a guide for us how to choose alpha or distance for this factor from the center. In most cases, rotatable design have a small correlation between the curvature terms. You know, uh, I don't know if you remember or not from the factorial design. Factors should be, as much as factors are more independent from each other, our model will be more accurate. So if for example, if temperature and time are not related to each other in as factor for our process or experiment, the result which we can get for the modeling of the process by these two factors will be more accurate than of two factors which are related to each, have a correlation between each other. So the if we use a rotatable design of experiment, it helps us to have uh, a small correlation between the curvature terms. Then it will help us to have a better model to describe the experiment. And also we can reduce this correlation even more by adding more center points. So the number of center points will increase the accuracy of the model as well. And with enough center points, the design can be rotatable as well. Let's go back to the CCD design. What is the general structure of a CCD design or CCD, central composite design? Usually in this design of experiment, we have factorial, axial point, and center point. And we need to have 2 power k factorial point. K is the number of factor. 2k star or axial points, and n3 as the center point of that. Let me show you what we have for, here is uh, matrix of experiment for an experiment which has 3 factors and it has 1 center. You can see you already, I think you know about the runs. Each one of these runs means you need to provide, you need to control x1, x2, x3 as your factors. For example, temperature, pressure, and humidity, for example. You need to control and provide uh, this amount of temperature, for example, 20 degrees Celsius, pressure 1 kilopascal, humidity 20% of humidity, and then run your experiment. It is one run of your experiment. Then measure, for example, the comfort level in a house can be the response, for example. So each one of these is one run for our experiment. I hope you know the run from the factorial design. So up to here, you can see it is similar to the factorial design. What we have added by learning or by introduction of the CCD design is this part, which is for axial points, and this is center point in this design. This is an experiment with 3 factors, and you can see the levels of the for this factor. 5 level, -1, 0, +1, negative 1.682 actually, -1, then 0, then 1, and finally 1.682. So we have that extreme low, low, medium, high, and extreme high levels for each one of these factors. Then, so you can see here we have 15 runs. We need to run our experiment for these 15 runs for different factors level, find the response for them, and then we can develop that second order model which can be used for optimization. We have also, we can categorize the or classify CCDs based on the location of the axial points. If the axial points are out from the factorial design space, we call design DCCD as CCC or circumscribed CCD. Each factor studied at 5 level, as you can see here, low, extreme low, uh, low, mid point can be here or here. It doesn't change anything, and high and extreme high. So 5 level for this factor. Also in this direction we have 5 levels. And as you can see here, axial point establish a new high and low range. In factorial design, high and low are these. For example, for this factor, x1, x2. For this factor, low and high are these 2 levels. for factorial point, but when we add this axial point, it changed to the these 2 point, the low and the extreme low and extreme high in this CCD, which we call that CCD. CCF is when we select the axial point and the surface at the center of each side of factorial space, like what you can see here. In this case, the maximum and minimum level for the factor doesn't change. But as you can see here, it is not rotatable because these points, these factorial and axial level or point are not located on the circle which circumscribe the factorial space. And the last one is CCI design for the CCD, which is inscribed CCD for the in this situation due to some limitation. I have discussed about, for example, we have x1 as our factor. So we select, level for that, x1 low, medium, and high, or low and high in factorial design. For example, temperature -20, high 20. Then we change it from factorial to CCD design. Then we need for this factor to have, for example, -30, -20, 0, 20, 30. So you can see here we have 5 levels, and we can have -30. However, in factorial design, the minimum level for this factor, which is temperature, was -20 degrees Celsius. We can also have -30 degrees Celsius. Then we can use this CCC design for our central composite design. But imagine x1 is time. Okay, do we have negative time? If in factorial design we have 0 second, then the next level is 20 second for factorial design. Then change to the CCD for time. How we can write something before this? We don't have negative value for time. So to add axial point to this factorial design, we have a limitation, which is that factor cannot be less than a specific amount. Like what? Then we need to change the design like this. In this design is for those situations where limit specified for each factor is real limit, like time. Beyond or below that level, it is not possible to perform an experiment. Like time, don't have negative time, can have also other examples. Then here also each factor is studied at 5 levels. In this design, actually, we need to select the extreme low uh, level for the factor at the minimum amount which we can have in the study. So here the minimum and maximum level of the factorial space is specified also by the minimum and maximum level for the axial. And actually it is a scale down of CCC design. If you compare them, you can see that this is a scale down of that. The structure is same, only the space which cover in design space by this CCC design is smaller than what we can have for CCC design. And as if you notice, both of them are rotatable, CCC and CCA, but CCF is not rotatable. We cannot draw that circle like what we have here. So this model is sensitive to and the model which can we can develop by this model is not that much accurate, and it may have higher error compared to what we have for CCC and CCI. If we compare these models, uh, as I said, CCC and CCI are rotatable, CCF is not rotatable, and the design space which is covered by CCI is less than what we can cover by CCI. So now, after we, up to here is the information about CCD design. Now let's start with BBD design. How is the box backend design? In this design, the difference with the CCD design here is we do not consider the uh, out the level out of the level which we have for factorial design. If you notice here, this cube is the uh, cube which we had also or which have for factorial design. We only change the position of the uh, point or level to the mid point of the edge of that factorial design. And this design is independent quadratic design and does not contain any embedded factorial or fractional design. If you notice here, we have changed that factorial design. Uh, in the CCD design, we have already the factorial point, but in the this design, BBD design, we have removed those factorial design. Then in this design, treatment combination are at the midpoint. As I said, they are at the midpoint of edge of the process space and at the center. So this design is like the value for each factor. This is a design space for a three factors design, and you can see here we have three levels for each factor. For example, for factor A, we have this, and this. And we have this for all of the factors. This design is also rotatable. You can see here we have a symmetry in this design, or we can say it is near rotatable. So our model is not sensitive to the direction of finding that equation or model. And each factor has three levels. Uh, Briefly, each factor is varied over three levels in this design, which is low and high, and also a medium value for the factor. It is also an alternative for that CCD design. If CCD design is not cannot be used for a RSM based design, we can also check BBD. And also the one problem with this design is it is not always rotatable. And also, if you notice, we can have combinations of two-level factorials for BBD design. If you compare with two-level factorials, also we can have that. However, I haven't presented that two-level factorial design. Here you can see a three-factor BBD with center point. You can see here we have three factors, A, B, C factor, and number of center point in this design is 3. Then our runs will be something like this: -1 for factor A, -1 for factor B, 0 for factor C in run number 1. And we need to go and do this experiment. This is the coded presentation of the factors actually. I can show you an example of this BBD example. You can see here is a real example. We are interested to know how the three factors as temperature, humidity, and light are effective on the comfort level in a imaginary room. This is BBD design. We can use BBD design, and then we need to select a level for that. Low, for example, 67, high, and center for the level which we have for temperature as one of our factor. And you can see also the levels for the humidity and also its unit and also for light. So you can see we have three levels for each factor in this box we can design. And you can see how we can implement that in this coded uh, table or matrix of experiment actually. -1 for factor A means 67 degree Fahrenheit. 1 means the high value for this factor. So here -1 is 67. 1 is the high uh, level of this factor, means it is 77. And 0 is the center amount for this factor, which is 72 degrees Celsius. And we can also write this for other factors. This is just coded one. And we need to run our experiment according to this table. In other words, we need to prepare a room, uh, use a heater, or we need control to temperature to put in 67, control the humidity, put in, here is a -1 means the low level, which is 30 percent, 30%, and C, which is light, here is 0 means medium, which is 10,000. So if you notice here we don't have that alpha, and we have only three levels: low, medium, and high. And we need to prepare a room and fix temperature, humidity, and light in these three values. Then prepare a questionnaire and ask someone to respond how is the comfort level in this condition, in this treatment. Then we need to change the temperature, humidity, and light for the other run, and again check the response and find the response for that. So you can see here a BBD design, how it can be useful. And also by this design, we can find that second order model as well. If you want to compare these two models, CCD and BBD, we can compare the number, the required number of runs is important because it will determine how many experiments you need to run, and it is effective on the time which you require for your projects, for your experiments, and also it is effective on the material which you need, the cost of your experiments. So lower values or lower runs which you can have for your projects or experiments means it is more desirable design of experiment actually. Then we can compare the CCD and BBD. As you know, both of them will give us that second order model. So we can compare them according to the number of runs. As you can see here, with three factors, an experiment with three factors, we need 15 runs. With CCD design, we need 13 runs with BBD design. And you can see also for four factors, again, the number of runs for DDD is lower, but for 5 and higher than CCD design will be higher. The number of the runs which is required is higher than BBD. But usually due to some advantages which we have for CCD, like what I have introduced to you, we can also check the outside of that factorial space. Then CCD design is more desirable method or design in RSM optimization or RSM design of experiment actually. So usually we use CCD and maybe otherwise we have a problem with the CCD like what I have discussed. If we have some limitation in the levels of the experiments of the factors, we may also go for BBD. So our first option is CCD. We cannot use that, then we can check BBD as well. So up to here is enough for this session. More explanation also can we will see in the software, and we will run a real experiment with this BBD and CCD. We will use real data and we will analyze those data according to both of these design. Thank you very much for watching this video lecture. Next session we will more discuss about how to evaluate the model which we can develop based on these two design. Thank you very much. See you next session.